So in the previous class, we have gone with the basics of different number systems, decimal, binary, octal, and hexadecimal we have seen, and also the conversion between each other we have already seen. This is the summary of what we have seen. So different number system is there: binary, octal, decimal, and hexadecimal. It's radix or base, different base 2, 8, 10, and 16. And what are the different numbers available, digits that is available with each of the number system, and their weights. So if it is integer part, so for integer part it is having 2 to the power I as a weight, and for the fraction part it is having the weight of 2 to the power minus f in case of binary. So okay, so if octal is there, it will be having base 8, so 8 to the power I, that means it is a positive power and a negative power will be there. So positive power for integer part, and for fractional part it will be negative powers. So we have already seen this. Next we will see is some operations on the binary digits. In terms of operations, the first binary: addition, subtraction, multiplication, and division we will see. So in case of addition, if there are two numbers, so one is 1011, another one is 1100. If these two numbers are there, we need to add. So for adding, 1 and 0 will be added, so it will be 1. 1 and 0, 1, 1 and 0, 1. And when 1 and 1 will be added, it will be 0 with the carry. So when there is 0 plus 1, it will be 1. When it is 1, 1 plus 0, again 1. If it is 1 plus 1, if this is the case, so it is 1 plus 1, it will be like 1, 0. So it will be 0 will be put here and 1 will be carry. 0 with carry 1. Okay, so this is how the addition will be done. So 0 plus 1, 1, 1 plus 0, 1, and 1 plus 1 will be, addition will be 0 with the carry 1. This is the case of addition. So similar way, this is there. So next one is, suppose we want to add another number, that is 0, 1, 0, 1, and added with 1, 1, 1, 1. So 1 and 1 will be added, so 1 and 1 will be added, it will be 0. So here the sum will be 0, but there will be a carry. So this carry is forwarded to here. So next location it will be forwarded. So if it is after addition of this location, the carry has been generated. So this carry will be forwarded further for further addition of the left side digits available. Okay. So 0 and 1 will be added plus a carry. So 0, 1 and 1 will be added. So it is like 0 plus 1 will be 1, 1 plus 0, 1 plus 1 will be again 1 plus 1 type is there, so it will be 0 with carry. So there will be a carry forward here also. So here again 1 plus 1 is added, that will be resulting you 0, and 0 plus 1 will be again resulting you 1. So 1 with a carry, so 1 plus 1 will be added, so a carry will be forwarded here. Again once carry is forwarded, 1 plus 0 is 1, again 1 plus 1 will be 0, and a carry will be forwarded. So this is how a binary addition is performed. So this is, you can remember. And similarly for subtraction, in case of subtraction, the subtraction will be like, if 1 minus 1 we are subtracting, the result will be 0. If it is 1 minus 0 we are subtracting, so 1 minus 0 will be subtracted with, that will be 1. But if we are subtracting 0 minus 1, that means we are subtracting 1 from 0. In that case, the result will be 1, and it will be 1 with a carry or with a borrow. Here we will be calling it. So from 0 we cannot subtract 1. So what we will do is, this 0 will be opting for a borrow. So a borrow will be taken. So borrow will be making it, instead of 1 it will be making it 1, 0. So from 1, 0, 1 will be subtracted. Okay, so it will be resulting you out 1 as a result, and this will be there with a borrow of 1. If borrow has been taken, then only this result will be there. So from 0 we cannot subtract 1, so we need to take the borrow. So similar is the case in case of decimal also. If we want to subtract 10 or suppose 9 from 5. If we want to subtract 9 from 5, then we cannot subtract it. So what we do is, it will take a borrow from the previous digit is available. So it will take the borrow, so that borrow will be making it to 15. Now after borrowing, it will take 10 as the borrow and total will be 15. So now 15 minus 9 we will be performing, and the result will be like with a borrow. So now we can subtract it. So similarly the case, if it will be taking the borrow, that borrow will be making it 1 0. Like here, if it is taking the borrow, it is making it 1 5. So we will be making it 1 0. From there we will be 1 0 means 2. 1 0 is in decimal, it will be 2. So from 2 we are subtracting 1, so 1 will be there remaining. So that's why here 1 will be there. So this is how we will be performing the subtraction. So suppose a number is there 1 0 1 0, and we are subtracting 0 1 1 0 from this above number. So to subtract that, it is 1 minus 0. So when it is 1 minus 0, 1 minus 0, it will be 1. If it is 1 minus 1, it will be 0. But when it is 0 minus 1, 0 minus 1, so it will be taking a borrow from here. It will be taking a borrow from here. Okay. So once it is taking a borrow from here, it will be 1 0. So from 1 0, it will be subtracting 1. So it will be 1 remaining. But once it has given the borrow, it is remaining now 0. So 0 minus 0, it is 0. So this is how the result we will be getting in case of subtraction. Next is multiplication. So similar to decimal multiplication that we have already known, similar we can do in case of binary also. So if two numbers are there, 1 0 0 1, and we are multiplying with 1 1 0 1. So the method that we perform for decimal multiplication, we can do the similar in case of binary. So this is how we will be performing, multiplying each digit with the above one and placing it one digit leftward, and finally we will be adding all, and after adding all we will get the result. This is how the final product we will be obtaining in case of multiplication of binary digits. Next one is division. So similar approach of the decimal case we can apply. So this is dividend, that is to be divided by a divisor, that is 1001. So we will be just considering the division. So here 1 times it will be going, so 1 times we will be making it, so 100, and then we will be subtracting it. So after subtraction we will getting 101. So again one digit will be placed here, and it will be 1011. So 1 times it will again go, and there we will again do the subtraction. 1 0 will be remaining, so to further divide we need to take 0 times, and 01 will be placed here. Now we will go with 1 times again, and this is the remainder coming out to be 0. So this is your remainder, this is remainder, this is divisor, and the result will be the quotient 1101. That is the quotient, and this is dividend, to which we are dividing by divisor 1001. So similar approach we can use in case of binary division also. So I hope it is clear with you. So the similar approach we can apply in case of octal and hexadecimal also. So the next point we will see is signed representation of numbers. So signed representation is basically, in case of a signed representation means we are going to represent a number either in positive or in negative form. So there are different methods to represent a number in negative or signed representation or a data representation, we can just see. So signed representation is done in 3 different ways. So one is like signed representation in terms of sign magnitude representation. One is one's complement. One's complement is the method through which we can represent a negative numbers or signed numbers. Next one is 2's complement. So by using the 2's complement method also we can represent a number in positive as well as the negative number representation. So we will see one by one what is a signed magnitude representation and what is 1's complement and 2's complement. So if we take the first one, that is signed magnitude. So in signed magnitude representation, the method that we will be using is here. In case of signed magnitude representation, if any number is written, suppose plus 7 is written. So plus 7 in case of binary, if we want to represent, it will be represented by 111. Okay. And if a number is there, that is 25 is there. So if we want to represent 25, so 16 and 8 will be added to 24 plus 125. So this is the representation. So if we want to represent this 7 in negative number, that is -7, we want to represent, and 25 in -25. So here in case of representation, so if number is represented by 3 digits, so 7 can be represented by 3 binary bits, but to represent -7 we need one extra bit. Okay, so if any number is there, that is 7, it can be represented by 3 bits, but to represent the same number in signed magnitude representation we need one extra bit, one extra digit, binary digit. So to represent it we will be adding an extra, that is 0 in case of positive number. Okay, and similarly if we want to represent the negative number, what we will do is just instead of 0 we can place 1, and the remaining 111 will be the same. So 111 is the representation of 7 plus 7, but to represent it in minus we will be adding one extra bit, that will be your sign bit. This is called sign bit. Here is also, this is sign bit. So if sign bit is 0, then the number that it will be representing is a positive number. If sign bit is 1, it will be representing a negative number. Okay, so similarly the case in case of 25, so 25 can be represented by 5 bits. It requires 5 bit to represent 25. To represent 25 in signed magnitude, we will be requiring one extra bit. So one extra bit is here 0, that will be your sign bit. This is your sign bit. So this sign will be bit is 0, then it will be positive number, and if we want to make it negative -25, we need to make it 1. So sign bit will be made to 1, and the remaining bits will be written as the same. So it will be 1 1 1 0 0 1. So this will be your -25 representation. So this is how we can represent a number in signed magnitude representation. So for representing a signed magnitude representation, we need an extra bit. Okay, so this can be a disadvantage of signed magnitude representation. The next one is 1's complement. 1's complement representation. So in case of representation, so complement representation is basically used for representing a negative number. Okay, so if 1's complement is there, another one is 2's complement. So it, in general sense, we can call it like, it is like r's complement, r minus 1's complement. So this complement representation can be applicable for either of the number system, either it is binary, either digital or hexadecimal or octal. So if we talk about the digital decimal case, so r's complement is, it will be written as 10's complement. If it is r minus 1 means we will be calling it 9's complement in decimal. Similarly in binary it will be represented by 2's complement or 1's complement. This is in binary. This is in case of decimal. Similarly if you talk about the octal case, it will be 8's complement or 7's complement. This is an octal. Similarly, we can represent in terms of hexadecimal also. In hexadecimal, it will be like instead of 8, we will be making it 16's complement or 15's complement. So 15 is here F. So F is represented by 15. So we will be making 16's complement or F complement. So that will be our hexadecimal complement. So 1's complement, 2's complement we generally used because in computer system we use the binary digits to represent the number. So binary method is used for implementing a computer system. So there, that's why we most frequently used 1's complement or 2's complement. But there is a complement of 10's complement and 9's complement also, or 8's, 7's, 16's and 15's complement. So these are based on the different type of number system. So that's why we will just see the binary complements, that is 1's complement and 2's complement. So I hope it is clear to everyone. So next, once we are going to have 1's complement or 2's complement, we will represent like how we will be representing a 1's complement and 2's complement. So if any number is there, suppose 1 1 0 0 1 is there, we want to represent its 1's complement. So its 1's complement will be just we will be complementing each of the bit. So if it is 1, we will be making it 0. If it is 0, we will be making it 1. If it is 0, we will be making it 1. If it is 1, we will be making it 0. If it is 1, we will be making it 0. So 1's complement of this number will be this. So 0 0 1 1 0 will be the 1's complement of this number. Okay, so I hope it is clear. So this is the direct method that I have let you know. Another, you can say, generalized method is, so generalized method is here to get the 1's complement. The generalized method that we use basically here is, it is r to the power n minus 1, r to the power n minus 1 minus the number that we want to get the complement. So this is the number, n is here, this number we not need to have the r 1's complement. So 1's complement is, so r is here radix of the number system, it is a binary, so it is 2 to the power n will be there. So 2 is the radix, so it is 2 to the power n. N is the number of digits. So 1 2 3 4 5 digit is there in the number, so it will be 2 to the power 5 minus 1 minus n. So n is this number, so it is 2 to the power 5 minus 1 is what is this? This is coming out to be 2 to the power 5. We can represent it like it is 32. It will be 32 minus 1 minus the number. So number is 11001. So if we make it, so it will be this minus 1, it will be taking one borrow, or okay, it is 11111. So this will be this minus 11001. So if we subtract this from here, it will be nothing but this only. So it will be coming out to be 00110. So this is the generalized method. This is the generalized method to calculate the 1's complement or r minus 1's complement. So r minus 1's complement will be represented by this in generalized sense. This will be represented by this will be applicable for all the type of number systems. So this is how we will be calculating the 1's complement. So the direct method is just we will be complementing the each digit. So it is 11001. So we will be complementing each digit. It will be giving out the 1's complement. Third one is 2's complement. So the direct method for calculating the 2's complement is, whatever the number is there, that is 11001, if we want to calculate the 2's complement, first we will calculate the 1's complement. So 1's complement is the complement of this, like 0, 1, 1, 0, 0. This we have calculated here. So whatever the 1's complement has been calculated, add 1 to this 1's complement, the resulting will be your 2's complement. So 1, 1 will be added, that is 1 and 0 will be added 1, 1, 1, 0, 0. So this will be the 2's complement of the given number, this. So for 2's complement, first we need to calculate the 1's complement, and then we will be adding 1 to it, and that will give us the 2's complement. So the direct formula in case of the generalized formula in case of 2's complement calculation, or R's complement calculation. So R's complement calculation formula is direct here. So that formula gives us, instead of whatever similar formula will be there, we will just be adding 1. So in that formula we will just adding 1, so it will reduce to, if we are going to add here, so it will be reduced to r to the power n minus n. So we are going to add this 1 into this formula. So after adding, it will be reduced to this only. So this is the formula to calculate the R's complement. To calculate R's complement, and this is for calculating the R minus 1's complement. So this generalized formula will be applicable for all the 4 different type of number system, and this formula will also be applicable for all this number system. So by using this formula also we can calculate by putting this value. So 2 to the power n is there, so 2 to the power n, that will be 2 to the power 5, so it will be 1 0 0 0 0 0. This will be 5 zeros. Okay. Next is n is the number minus 1 1 0 0 1. So that means from this number 2 to the power n, so n will be 1 2 3 4 5 digits are there, so 2 to the power 5 will be there. So that will be this representation minus this. So minus, to subtract this, what we can do is we will be writing it here. So just subtract it 1 1 0 0 1. So just subtract and get the result. So to subtract, it will be taking a borrow from the previous ones. It will be 1 0 minus 1 will be 1 will be the here, and again here it will be taking the borrow, because it has, once it is going to take from here, the borrowing will be like, if it wants to take the borrow, it is not having, it will be taking from here, it is not having, and then it will be taking here. So from there the borrow will be coming out to be here, then it will be 1 0 again, that will be taking. So here 1 is remaining. So like suppose in the case 1 0 0 0, and from there we want to subtract suppose 2 in decimal. So this is the case of decimal. So if we want to subtract, so here we consider is it takes the borrow from here, here, and from here. So from here it is taking the borrow, so it is going 10 here, then here. So finally here 10 is there, out of 10 we are subtracting 2, so 8 will be remaining, and then it is having 9. We place it here 9, and here it is having 9. This is how do in decimal. So similarly the case. So here once it is going to take the borrow, all in between digits will be taking 1 1 1 1 will be there. So 1 10 minus 1 0, that is 2. 1 0 minus 1 will be 1. Here 1 is remaining. So 1 minus 1 1 minus 0 is 1. 1 minus 0 is 1. Here is 1. 1 minus 1 is 0. 1 minus 1 is 0. So these two are same. So either we can use the shortcut method, that is by calculating the 1's complement and adding 1, we can get the 2's complement, or we can use the formula r to the power n minus 1 minus n will be giving out the 2's complement. So I hope it is clear to everyone. So this is how we have got the 1's complement and 2's complement. So 1's complement and 2's complement and sign magnitude, these are to represent the negative numbers. So we can just summarize all the representation. This is how we can summarize it. If a binary number is there, it can be represented by a sign magnitude, or 1's complement, or 2's complement. So here a decimal number is there. So different decimal number respect to this, there is a sign magnitude representation and 1's complement representation and 2's complement representation. So we can just see So if it is 0 is there, so we'll be representing in sign magnitude 1's complement and 2's complement, the same 0 is represented. If it is 1, so to represent 1 can be represented, this has taken the 4-bit sign magnitude representation. Why? Because the 7 can be represented by 3 digits, 3 bits. So 1 bit will be the sign magnitude, so that's why 4 bit has been taken. So 1 will be represented by 0 0 0 1. So for 2 it will be 0 0 1 0. So for all the positive numbers, so up to here these are the positive numbers. So you can just see the MSB bits are there. So all the positive numbers have the MSB bits 0. Similarly, in the sign magnitude representation, all the negative numbers is having the MSB bit, that is 1. So 1 means it is having a negative number. This is the representation of sign magnitude, and the remaining will be the same. So 0 is there, so you can just see. So 0 can be represented by 0 0 0 0 also, and minus 0 is represented by 1 0 0 0. Okay, so a 0 representation has been represented by 2 different signs. So this is the disadvantage of sign magnitude representation. It can have 2 different representation of 0. So this is not a good, you can say, a technique to represent the numbers in negative form. Similarly, in case of 1's complement also, we can just see. So to represent the 1's complement, the positive numbers will be having the same relation. So whatever the positive numbers are there, whatever the binary representation is there, same with the 1's complement. Similarly, is the 2's complement. So 2's complement will be having the same representation, that is having the binary representation only. So up to the positive numbers, it is the same representation in case of signed and 1's and 2's complement. But in case of negative, if you want to represent a 0, minus 0, so again here, so to represent minus 0, we will be complementing the 0. So 0 is 0 0 0 0, complement of it is 1 1 1 1. So again 0 is having 2 different representations. So this is the also the disadvantage of 1's complement. And if it is 1, so whatever the 1 is there, 1 is represented by 0 0 0 1, so its complement, we will be making its complement, so it will be 0 1 is 0 and 1 1 1. So its complement is the 1's complement. So this is how the representation will be there. So if we want to consider the case of 8, suppose 8 is there, so 8 is 1 0 0 0. This is the 7, up to 7 it is representing. But in case of 8, if we want to have, so 8 will be this. Okay, so 8 is, if this is the 8, and if we want to make the complement, so it will be 1 1 1 and 0. Okay, but this is 8 is not represented in terms of 1's complement, because its range is basically limited to whatever the representation. If 4-bit representation is there, it will be representing only the magnitude terms only. So it is like 4 bits is there, so 3 bits will be only representing the magnitude. So up to 3 bits only we can represent the magnitude. So that's why minus 8 cannot be represented in the case of 1's complement. Similarly, in 2's complement, we can see up to here we have the same. But in case of 2's complement, if we want to have 2's complement is 1's complement plus add. If we plus 1, we will be making plus 1, then it will be coming out to be a 0 0 0 again. So it is same. So 0 can be represented by only one type of representation in case of 2's complement. So that's why 2's complement is preferred in all different types of applications. If we are going to perform mathematical operations, so 2's complement is preferred because it is having single representation for 0. Okay, and also it is applicable, like it can represent minus 8. So minus 8 can be represented by 2's complement representation. Okay, and all other methods are same, like we will be adding here 1, so it will be making it 2's complement of minus. Some of the arithmetics we will see is addition and subtraction by using 2's complement. So we have taken the example. Suppose we have a 2 number, that is 48. We need to subtract it. Okay, so 48 minus 23 we need to do, and because we prefer performing the mathematical operations by using 2's complement. That's why we have taken the example of 2's complement only. So 48 minus 23 we need to perform. So this we can do by using, like, we know the addition. Okay, so we can do addition easily. So 48 and plus, what we can do is minus 23 we can write. So 23 is there, we will be writing it as minus 23, and minus 23 we will be adding with 48, then it will be representing the subtraction part. So here the addition is basically used for doing the mathematical operations. So all the mathematical operations will be done with the help of additions only. So 14 is there, 48 is there, we will be representing it its 2's complement. So 48 2's complement will be this representation. So this is how we will be representing the 48 in 2's complement, and 2's complement of 23. So 2's complement of 23 is this. So first of all, in case of 2's complement representation, we will be doing it 48. So 48 2's complement will be same as the binary 48, because we have already seen previously, like, for positive numbers, whatever the binary representation is there, the 2's complement representation will be the same. So in case of addition of 48 plus minus 23, we need to make the 2's complement of 48 or direct binary representation of 48. So it is binary representation. And to subtract 23, what we need to do is we are going to represent 23 into 2's complement. So 23 we are representing in 2's complement, so it will be a negative number. So first of all, we will be writing 23 into binary, and then we will be applying the 2's complement. So that will give us minus 23 in 2's complement. Okay, so it will be minus 23 into 2's complement. So once we have minus 23 in 2's complement, we will be adding those two numbers. So addition will be performing. So 48 and minus 23 represented, we will be adding. So after adding, whatever the result is coming out, that will be having a carry. If a carry is there, we will be discarding the carry. So in case of 2's complement, if addition is to be performed by using the 2's complement, whatever the result is there, into that if a carry is generated, we will be neglecting this carry, or we will be discarding this carry. So the result will be this 0 0 0 1 1 0 0 1. So this will be giving out the plus 25. So this will be our result. Similar is the example if we are doing 23 minus 48. So next is we are performing 23 minus 48, or we will be performing by considering like 23 plus minus 48. So we will be writing 23 in 2's complement, then taking the 2's complement of 48, that will be representing the minus 23. 2's complement of 48 will be giving out minus 48, sorry. So then whatever the 2's complement is there, we will be adding it, and it will be giving out the result. So similar is there. So 23 will be represented by the basic representation, binary representation of 23. For 48, this was the binary representation. We will be taking the 2's complement of here. So 2's complement of 48 if we take, so for that, first of all, we will taking the 1's complement. So if we take the 1's complement, we will be complementing it further. So it is 1 1 1 1, 4 1s will be there, and then 0 0 and 1 1, 0 0 1 1. So this is your 48 1's complement. We will be adding 1 to it. So it will be 1 1 is 0, then 1 carry. So 1 1 is 0, 1 carry, 1 1 is 0, 1 carry, 1 1 is 0, 1 carry is 1, then 0 1 1. So this is the representation. So similar is there. So this is the 2's complement, 2's complement of 48. So if 2's complement of 48, this will be representing the minus 48. The 2's complement of any number will be taking it out to the negative number. So this is minus 48. So minus 48 is added to 23. So if we are going to add it, we can get the result. We can just add it and we can just see like there is no carries there, no carry. So if there is no carry, that means whatever the number is there, this number is in 2's complement. So if it is in 2's complement, we need to take again the 2's complement so that we can get the result. Or we can get is like if it is in 2's complement, here it is giving out the 1 is there, that means it is representing the negative number. If we take it out, we can just see like it is the 2's complement representation of 25. Or we can just take the 2's complement further. Suppose we want to take the 2's complement. So what we will be doing is, first of all, we will be complementing it by using the 1's complement. So 1's complement is 0 0 0 0 0 0 1 1 1 1 and then 0 0 0 0 0 0. So this is 1's complement. We will be adding it further. So that will be 1 0 0 1 1 0 0 0. So what is it representing? It is representing the plus 25. That means before taking the 2's complement, what was the number? So this number was minus 25, because after complementing it, it is giving out plus 25. That means before complementing it was minus 25. So output is represented in 2's complement. But in the previous case, you can just see if there is a carry, if carry is there, then the number that is representing is in binary. So the result will be in binary, and that will be like exact representation, or it is in binary, or it is also in 2's complement. But if it is 0 here, so 0 means it is a positive number. Here the result is in 2's complement, it is having 1 at the MSB side, that means it is a negative number. So to get the exact number that is a negative number in 2's complement, to get the exact number in negative, we need to again take the 2's complement, and it is coming out to be 25. So 25, it is in positive, and that means the previous one was minus 25. So I hope you have got the point. So the next example we can see, we need to perform 48 minus 23, that we want to perform. So that means what we can do is we can proceed further, and minus sign we can add, remove that is at minus minus, it will be a positive 23. So now it is normal addition. We will be just representing the 48 in binary and 23 in binary, and we will be adding, the result will be in binary. It is in positive is there, a positive number, because it is 0. So MSB is 0, that means it is a positive number, or it is positive number, that means the binary representation or 2's complement representation all are same. So whatever the exact binary decimal equivalent is there, that will be your plus 71. This is your result. Okay, so I hope you have got the point, like how we are going to proceed with the help of 2's complement, different arithmetics that we can apply. Okay, so next point we will see is different types of codes. So there are different binary codes are there. Further we will be proceeding like instead of different number systems, there are different type of codes that are there to represent the binary numbers. So one of the codes are like BCD code, that is binary coded decimal BCD codes, or one is XS3 codes, or another one is gray codes. So there are different codes in which the binary digits can be represented. So a binary digit is there, it can be represented in terms of BCD, XS3 or gray code. So to convert any decimal number, suppose it is 251, that is in decimal, we want to represent it into BCD. Then each digit of the decimal will be represented by 4 bits to represent its equivalent BCD number. So if it is 1 is there, so it is 0001 will be the BCD of 1. 5 is there, so 5 will be having 0101, that will be the BCD of 5. BCD of 1. BCD of 2 will be 0 0 1 0. So in 4-bit we will be representing these numbers. So this is your 2, this is 5, and this is 1, and this overall 0 0 1 0 0 1 0 1 0 0 0 1, this will be the BCD of 251, that is in decimal. So this is how we can represent a BCD number. Similarly, if it is an XS3 number, so whatever the BCD number is there, we will be adding 3 to it. 3 means 0 0 1 1. If we add in each digit 0 0 1 1 0 0 1 1 in each digit, the result will be like, if it is this, it is 1 1 is 0 1 1 0 1 0. So this is the first one. In the second one, it is 1 1 is 0 1 1 with a carry, that is 0 with a carry, 1 1 is 0 with a carry, this. And again here also it is coming out to be 1 1 1 is 0 and then 1 0. So this will be the XS3 representation of decimal number. Okay, so one thing we can see here, this XS3 is obtained from the BCD representation. So whatever BCD representation here, there we will be adding each digit of the decimal or each digit of BCD. So BCD is represented by 0010 for one digit of decimal. So we'll be adding 3 to it, and that will be giving out the XS3. So XS3, as the name suggests, it is extra 3 that is being added to the BCD representation. And the next one is gray code. So gray code is in the gray code. So whatever gray code will be obtained from a binary number. So first of all, we will be converting any number to a binary. Then we will be representing this binary number to gray code. So gray code. So I think you might have gone with the gray to binary conversion in the basic electronics lab also. You might have gone into that. So for conversion of binary to gray, if suppose this is the binary number, if you want to convert it into gray, what we will be doing is the first digit we will be representing as it is, that is 1. Then 1 and 0 will be doing the XOR of 1 and 0. So 1 and 0 XOR will be 1. So XOR of 1 and 0 will be 1, and again XOR of 0 and 0, this is 0. XOR of 0 and 1 will be 1. So this is the gray. So from there, binary, we can represent the gray. So the advantage of gray is, if we compare these two numbers, we can just see like there is only one bit change is there. Only one bit will be changing in these two representation. If it is binary, so from there will be only one bit change is there. If next gray is there, the next gray code will be only one bit change from the previous gray code. So this is the advantage of gray code, like it reduces the, you can say, the power dissipation. Even if we are going to use the gray code, it reduces the power dissipation, or it basically avoids the change in the large, like if there is there 0 0 0 0 is there. Okay, so if it is, suppose this is there, or it is 0 0 1 0, okay, or any representation is there, in that if it is 0 1 0 0, or suppose there is a change 0 1, so there is one bit change is there in between these two numbers. But in these two numbers we can see there is 3-bit change is there. So if 3-bit change at a time, it will be taking more transistors to switch from 0 to 1 1 to 0. So switching power in this case is going to increase. But in case of gray code, if we are using, there is only one bit is changing at a time, so there it reduces the switching power dissipation in that case. So this is how we will be representing a BCD, XS3 and gray code. So you can just summarize. We can just summarize like how if a binary decimal number is there. So in that with respect, we have a binary representation. So for 0 to 15, we can represent the binary number system. And then if we want to represent the BCD, so BCD is defined only with up to 0 to 9. So for decimal number between 0 to 9 only, it is representing the BCD, because BCD represents, like, each digit of BCD is represented by 4 bits. Okay, so each digit of decimal is represented by 4 bit. So up to 4 bit we can represent it, like 9 is considered to be here. If we want to represent the 10, so 10 will be represented by 10 in BCD. So 10 will be the 10. If you want to represent 10, it will be represented by 10 means 0001 and 0000. So this is the 10 in case of BCD. So up to 0 to 9 only the BCD is defined. And similarly, because XS3 is addition of plus 3 into BCD, so that's why XS3 is also defined up to this only. So if we want to represent this further, it will be adding with respect to that only, like XS3. And gray code is defined by the binary. So binary is there, we will be taking the gray code by taking the XOR gate. Okay, like if it is 0010 is there, so if it is 0010 is there, if you want to find out the gray code, so this is 0 again as it is put here, we will be taking the XOR of these two. So XOR of these two will be representing out 0, XOR of these two will be giving out 1, XOR of these two will be giving out 1. So it is 0011. So if it is 0010 is there, its gray code will be 0011. Okay, so similar, we can take another example also. If it is 1001, its representation in gray will be 1, it will be at stage 1. Then 1 and 0 will be XOR of 1 and 0 will be 1, XOR of 00 will be 0, XOR of 0 and 1 will be 1. So it is 1100, 1101. So it is 1101. This is the gray. So this is uh, all about your different codes that are used in case of binary. So binary representation is there. Binary is represented either in BCD, XS3 or gray codes. We can represent it. So up to here, if anyone is having any doubt, you can ask. So in the next class, we will see the Boolean algebra.